Hello and welcome back to What's Up Physics. My name is Mariah, and today we'll be doing an introduction to forces. What is a force? A force is a push or a pull on an object caused by its interaction with another object. Forces are vector quantities and are measured in newtons. We've already seen some forces in the kinematics unit, like the gravitational force. We've also seen different objects apply forces to each other. For example, in the 2D motion and projectiles video, one of the problems dealt with a cannon firing a cannonball. The cannon exerted a force on the cannonball that caused it to shoot out from the cannon. And there are two types of forces that we'll be working with: contact forces and non-contact forces. First, we'll go over the contact forces. First, we'll be going over the normal force, and when we're labeling it, we'll be writing it as F sub n. The normal force is a perpendicular force applied on an object by a surface it is in contact with. If the normal force didn't exist, you wouldn't be able to stand on the floor. You'd go right through it towards the center of the earth. The normal force from the floor pushes you upwards so that you can touch the floor, but you can't move through it. The normal force is caused by electromagnetic repulsion. You'll learn more about this in physics too, but basically, there are electrons in the floor and there are electrons in your body. Electrons carry negative charge, and since like charges repel, the electrons in the floor and your body repel each other, which prevents your body from sinking into the ground. We've got some examples over here of this box touching different surfaces. For each example, we're going to draw the normal forces acting on the box. Looking at this box on the top right, we can see that it is sitting on a flat surface. Since the surface is flat, the normal force would be applied directly vertically to the box, because that is perpendicular to the horizontal floor. Now let's look at the box in the middle. It is touching two surfaces, this wall and this floor. How do we draw the normal force now? The box touches the floor like this, so the floor exerts a perpendicular, and in this case, vertical normal force on the box. The wall touches the box like this, so the wall exerts a perpendicular, and in this case, horizontal normal force on the box. Lastly, we've got this box on the bottom. It's on an incline. How should we draw the normal force now when the incline is touching the box at an angle? The incline is touching the box like so it would exert a force perpendicular to that line on the box. Here's one more fun problem. We've got a roller coaster, which is the demon from Six Flags if you're wondering, with a loop-de-loop, and right now the cart is upside down. How do we draw the normal force the track is exerting on the cart? Well, the cart is pretty long, so we're just going to represent it at one point here. The cart, sorry about that, technology. The cart touches the track like this. And since we know the normal force acts perpendicularly to how the two objects touch, we know that it would look something like this. Now let's talk about the friction force. When we label this force, we're going to write it as F sub F. The friction force acts to resist the sliding of two surfaces past each other. If you take your hands and push them hard together and then rub them back and forth, you'll notice that they don't slide very smoothly against one another. This is because there's a lot of friction between your hands. Your left hand is exerting a frictional force on your right hand, and your right hand is exerting a frictional force on your left hand. We have an equation for the friction force here, which states that it is equal to mu times the normal force. Mu is the coefficient of friction, which measures the amount of friction between two surfaces. So it's a property of the two surfaces, and it won't change unless you change the surfaces themselves. Mu doesn't have any units, and it is typically a number between 0 and 1. If there's a lot of friction between the surfaces, like if they're coated in sticky honey, mu will be closer to 1. In fact, it can even be more than 1. But if there isn't a lot of friction between the surfaces, like if it's a box sliding on ice, mu will be closer to 0. There are two types of friction and two types of mu which will correspond to those types of friction. There's static friction and static mu. And you indicate that by writing F sub S, and then for mu, it's the mu symbol, sub S. And there's also kinetic friction and kinetic mu, for which you would write F sub K and mu sub K. What is the difference between the two? Static friction is typically present when an object is at rest. It prevents objects from moving even while another push or pull is acting on it. For example, if you look at this box on the incline, the gravitational force would make it slide down, except it could be counteracted by an equal amount of static friction. And this would keep the object from moving. Another example is pushing something heavy, like a dining table. It won't move immediately when you start pushing. You have to increase the amount of force you are applying until some threshold is hit, and at that point the table would move. This is where the concept of maximum static friction comes into play. It's the maximum resistance friction can put up to stop an object from moving. If you apply a force to an object and it is smaller than the maximum friction, friction will match that force in size, because that's all it needs to do to keep the object from moving. If you increase your force, the frictional force will increase to match that until your force is greater than the maximum friction. Once that happens, friction cannot match your force and you will be able to move the object. And this is what we mean when we say that the static friction force only acts as hard as it needs to stop the object from moving. Now, if the object were to start moving, then kinetic friction would be acting on it. Kinetic friction is present when slipping, the movement of two surfaces past each other, occurs. The only time that there would be static friction when an object is moving is if that object is rolling without sliding, but this is something we'll talk about in a later unit. For now, just know that if there's friction when an object is moving, it's kinetic friction, and if there's friction when an object is at rest, it's static friction. Now let's say that we've got this box here, and it's moving to the right and slowing down. This is a good time to bring up that the reason a random sliding object, like your phone on your desk, would slow down and come to rest is because of friction. Otherwise, it'd just keep on sliding forever. If the box is moving to the right, then friction needs to be applying a force in the opposite direction to slow it down. And it's kinetic friction. Lastly, here is a picture of a penguin sliding on ice. I put it here firstly because it's cute, and second because this is a great time to tell you how to know friction can be ignored in a problem. If so, the College Board will either say that friction is negligible or use a keyword to clue you into the fact that there's no friction. They might give you an example where an object is sliding on a smooth surface or where an object is sliding on ice. On the other hand, if a problem states that friction is non-negligible or that the object is moving on a rough surface, then friction cannot be ignored. Now let's talk about the applied force, and the notation for this one is F sub A. This is a force that acts directly on an object and its parts, rather than through an external object like a cable. For example, if you've tied a rope to a cart and are pulling the rope, then you're applying a tension force, which we'll talk about in just a second. But if the cart that you are holding has a handle that you're pulling on, then you're using the applied force on it. This is basically a garbage dump for pushes and pulls that don't fit into the other categories. Now let's draw the applied force that this little boy applies to the cart of pumpkins. What would this look like? By looking at the handle, we can tell that he's pulling the cart at an angle, and that is the same angle that his applied force vector should be drawn at. Now, let's draw the applied force that this kiddo applies to a sibling stroller. What would this look like? He's a short kid, so he's going to be pushing the cart strictly horizontally, from his perspective at least. But if he were taller, if he looked something like this, maybe, then he'd be pushing the cart both horizontally and down. So now his applied force vector would look more like this. That is a horrible color, my apologies. It would look more like this. Next up is the tension force, and the notation for this one is F sub T. The tension force is caused by a pull done through a string or a cable. It can't be a push because you can't push objects with a rope. Typically, we will be dealing with ideal ropes, which have negligible mass, don't stretch under tension, and have equal tension at all points. Strings with non-negligible mass might have varying tension at different points in the string, but you won't need to worry about these as you're never expected to do calculations involving non-ideal strings. We will also be working with ideal pulleys, which have negligible mass and rotate while experiencing negligible friction. Don't worry about non-ideal pulleys, they won't show up on the exam. If you look at the first picture, then you'll see this dude, and he's pulling a chest with a rope. He's tugging the rope up and to the right, and so that is the way that the tension force points. Now let's look at this second picture here, and at the bucket to the left. The rope is drawn around a pulley and connects to the bucket at 2 points. The rope thus pulls the bucket up at these 2 points, which is why you draw 2 tension force vectors, one for each part where the rope is suspending the bucket. To clarify, there is only one tension force in the rope. There can't be multiple amounts of tension force in a single rope. But we draw two tension force vectors on the bucket because the tension in the rope is being applied to the bucket in 2 different points. There's no reason one object can't apply multiple forces on another object. For example, a box sliding on a rough surface would have two forces applied on it by the surface, a normal force and a frictional force. It's the same concept here. And now we've come to the spring force, and you can write this as F sub S or F sub SP, whatever. The spring force is the force applied by the attachment of a spring. Yes, springs can also push or pull on objects. And here we've got our equation for the spring force, and we won't be using it for a while, but if you wanted to know, the spring force is equal to -1 times the spring constant times the spring's displacement from equilibrium. And equilibrium is the position where the spring is unstretched or uncompressed. The spring constant is a property of the spring that tells you how strong or weak the spring is. If you've got a spring that's hard to stretch or compress, it's got a higher K value than a spring that's easier to stretch or compress. The spring force always wants the spring to return to the position where it would be at equilibrium, so it acts opposite the direction of displacement. For this picture down here, you can see that there is no spring force as the spring is not displaced from equilibrium. For the top left picture, you can see that the spring force acts towards the right because the spring is displaced to the left of the equilibrium position. And for the top right picture, you can see that the spring force acts towards the left because the spring is displaced to the right of the equilibrium position. And here the magnitude of the spring force is greater than over here. And this is because the spring is more greatly displaced. Now let's talk about air resistance. And the notation for this one is F sub air. Air resistance is the drag or resistance force applied by the air when you drag an object through it. We've already talked about this a little in the kinematics video while discussing freefall and terminal velocity. Freefall is when an object is moving through the air and it has no air resistance acting upon it. And terminal velocity is when the air resistance force acting upon an object is equal in magnitude but opposite in direction to the gravitational force acting upon that same object. Air resistance is also what allows us to use parachutes. See, parachutes, they trap air underneath their sails, and that air pushes back on the parachute by applying air resistance to it. This slows down the parachuter's fall and allows them to land safely. And now we're on the buoyant force, and you would write this as F sub B. The buoyant force is the net upward force exerted on an object by a liquid. In other words, it's a combination of the forces exerted on the object by all of the particles that make up that fluid. The equation for the buoyant force states that the buoyant force equals the fluid's density times the acceleration due to gravity for whatever planet you're on times the fluid's volume. Let's look at this picture on the right. We've got two balls and one is floating while the other is sinking. You can see by looking at the weight vectors that the pink ball is considerably lighter than the yellow ball, right? This one has a bigger weight vector. The buoyant force is equal in magnitude to the weight of the pink ball, and so it is able to keep the pink ball afloat. However, the weight of the yellow ball is greater than the buoyant force, and so the ball sinks. Note that the buoyant force is constant no matter what object is placed in the water. Whether it sinks or floats is determined by the object's weight. Now we'll talk about the types of non-contact forces. In AP Physics 1, you'll only be dealing with one non-contact force, and that is the gravitational force. You would write this as F sub G. The gravitational force attracts any two objects that have mass. It is attractive because it pulls objects together and never pushes them apart. Our first equation for the gravitational force is that it's equal to the mass of the object times the acceleration of gravity. You'll often hear the gravitational force being referred to as weight. This is because an object's mass times the acceleration of gravity is equal to its weight, measured in newtons. Have you ever heard about how you would weigh much lighter than you currently do if you were on the moon? That's because the moon has a lower acceleration of gravity than the Earth. Your mass will never change because it's a measure of how much stuff you are made up of, so the acceleration of gravity is really what determines your weight. Here we've got a second equation, which states that the gravitational force is equal to the universal gravitational constant G times mass 1 times mass 2 divided by the radius squared. Mass 1 and mass 2 are the masses of the two objects that we are trying to measure the attraction between. And r is the distance between the centers of the two objects. Now, what is the difference between the two equations? The first one is used specifically to calculate the gravitational force a planet exerts on objects on or near its surface. The constant g represents the acceleration due to gravity and varies from planet to planet. On Earth, g equals 10 meters per second squared. The second equation is used to find the force of attraction between any two objects. Now let's try and draw the gravitational forces vectors for two scenarios. For this first one, we've got a block on an incline and it's moving down the slope. Which way does the object's weight point? It must point down the slope, right? Wrong. The gravitational force that we're talking about is the Earth's pull on the slope. The Earth pulls not in an angle, but straight downwards towards its core. But then why does the block move down the slope and not through the incline? Just like with velocity, forces can be divided into horizontal and vertical components. Like so. And this horizontal component is what causes the block to move down the slope. But then wouldn't the block go through the incline because of this vertical component? No, because the incline is exerting a normal force on the block that cancels out that vertical component's effects. We'll talk more about components in our next video. And for our last example, remember that an object's weight is just the gravitational force that is acting on it. And from the equation, the gravitational force is equal to the mass times the acceleration of gravity, we can see that the ball on the right has a greater mass, as its weight is greater and the acceleration of gravity is the same for both objects. Our next lesson will be on Newton's first and second laws, and we'll also be teaching you how to draw free body diagrams. If you like this lesson, please consider liking, sharing, and subscribing. See you next time!